On a frozen morning in Kazakhstan, Soviet engineers ignited a rocket engine that burned hotter than the surface of a star. The RD-0410 nuclear thermal rocket, a machine that used a live nuclear reactor as its beating heart, achieved what American scientists thought impossible: a specific impulse of 910 seconds, crushing the performance of NASA's best nuclear engine by a comfortable margin. For a brief moment, the Soviet Union had won the ultimate prize in the space race, the key to Mars and beyond. But this wasn't just a triumph of engineering. It was a gamble with consequences that could have dwarfed Chernobyl. To understand why this engine represented such a pivotal moment in the Cold War, you first need to understand what makes nuclear thermal rockets the holy grail of space propulsion. Imagine you're trying to reach Mars using conventional chemical rockets, the kind that powered the Apollo missions to the moon. You're essentially burning sophisticated kerosene or hydrogen with oxygen, creating hot gas that shoots out the back of your spacecraft. It works, but it's fundamentally limited by chemistry. The molecules can only get so hot, only move so fast, before the laws of thermodynamics say, that's it, that's all you get. Now imagine a different approach. Instead of burning fuel, you take liquid hydrogen, the lightest element in the universe, and you run it through the core of a nuclear reactor. Not near it, not around it, through it. The reactor heats that hydrogen to temperatures that would vaporize steel, turn tungsten into vapor, make diamonds sublimate into carbon gas. Then you expel that superheated hydrogen through a nozzle, and suddenly you're playing a completely different game. You've nearly doubled your efficiency. Where a chemical rocket might give you 450 seconds of specific impulse, a measure of how effectively you're converting propellant into thrust, a nuclear thermal rocket could theoretically deliver 900 seconds or more. This isn't just an incremental improvement. This is the difference between Mars being a distant dream and Mars being a destination you could reach within a human lifetime, literally. With chemical rockets, a round trip to Mars takes over 2 years, exposing astronauts to cosmic radiation, bone density loss, and psychological stress that pushes the limits of human endurance. With nuclear thermal propulsion, you could cut that time in half, maybe more. You could make Mars missions not just possible, but practical. The Americans understood this. In 1963, NASA and the Atomic Energy Commission launched the NERVA program, Nuclear Engine for Rocket Vehicle Application. Over the next decade, they would spend approximately $1.4 billion developing nuclear rocket technology. By 1969, American engineers had achieved specific impulse values between 825 and 850 seconds with their hot bleed cycle design, and were projecting 850 to 875 seconds with an improved expander cycle configuration. They built test reactors. They fired them at the Nevada test site. They proved the concept worked. But across the Iron Curtain, Soviet intelligence was watching, and what they saw both terrified and tantalized them. The space race had been defined by a series of Soviet firsts. First satellite, first human in space, first spacewalk, followed by the crushing American triumph of the moon landing. The Soviet lunar program had failed. Their N-1 rocket had exploded spectacularly, repeatedly. They needed something to restore their prestige, to prove that Soviet engineering could still lead humanity into the cosmos. Valentin Glushko, the influential chief designer at KB Energomash, saw nuclear thermal propulsion as that opportunity. Here was a technology still in its infancy, where American advantages in computing and miniaturization mattered less than raw engineering prowess and a willingness to take risks. If the Soviet Union could build a superior nuclear rocket engine, they could leapfrog American technological advantages and make Mars missions feasible within budget constraints that wouldn't bankrupt the state. The Americans had shown it was possible. The Soviets would show it could be perfected. But Glushko faced fierce resistance. Chemical rocket engineers, the establishment that had built the R-7, launched Sputnik, sent Gagarin into orbit, dismissed nuclear propulsion as too dangerous, too expensive, too far from practical deployment. Why chase this fever dream when proven chemical rockets could still accomplish so much? The debates within Soviet design bureaus grew heated. Nuclear propulsion was unproven. It was reckless. It was exactly the kind of technological moonshot that could destroy careers and waste resources that could be better spent on incremental improvements to existing systems. Then intelligence reports confirmed NERVA's progress. The Americans weren't just theorizing. They were building hardware, conducting tests, achieving results. Political pressure mounted from the highest levels of Soviet leadership. The Soviet Union could not afford to fall behind in yet another space technology. Not after the moon. Not when the propaganda value of being first to Mars could reshape the global perception of socialist technological superiority. The project received official approval. The man chosen to lead the technical development was Nikolai Konyukhov, a brilliant engineer at KBKHA Voronezh. Konyukhov was a perfectionist, someone who understood that the difference between a functioning nuclear rocket and a radioactive catastrophe lay in the precision of every weld, every calculation, every material's choice. He was also acutely aware that he was being asked to solve problems that had stymied the best American engineers, and he was being given less money and less time to do it. The challenge was brutally simple in concept, nightmarishly complex in execution. A nuclear thermal rocket requires a reactor core that can operate at temperatures exceeding 3,000 Kelvin while being bombarded by its own neutron flux, cooled by cryogenic hydrogen flowing at high pressure, and controlled precisely enough that it doesn't melt down or explode. The fuel elements, the actual uranium-containing rods through which the hydrogen flows, must maintain their structural integrity under conditions that would destroy almost any known material. The American NERVA program had struggled with fuel element cracking. Their designs used a graphite matrix with uranium carbide particles, and while this worked for short test firings, the thermal stress and neutron bombardment caused microscopic cracks that propagated over time. If a fuel element failed catastrophically during operation, you could have a partial reactor meltdown combined with a hydrogen explosion. Not ideal for a spacecraft. Konyukhov's team at KBKHA Voronezh, working with nuclear physicists from the Kurchatov Institute, developed an innovative solution. Instead of copying NERVA's approach, they would learn from its weaknesses. The RD-0410 design incorporated thermal insulation between the uranium carbide and tungsten carbide fuel elements and the zirconium hydride moderator. This allowed for a more compact reactor core while managing the extreme temperature gradients more effectively. But the real innovation was in the hydrogen flow pattern. Rather than flowing hydrogen directly through the hottest parts of the reactor first, the RD-0410 design cooled the moderator first. This maintained low neutron energy and high fission cross-section, keeping the nuclear reaction stable and controllable. Then the hydrogen made direct contact with the fuel rods, heating to extreme temperatures. To prevent chemical reactions between the hydrogen and the carbide fuel, reactions that could weaken the fuel elements, the engineers added hexane to the hydrogen. It was an elegant solution to a problem that had plagued earlier designs. The target specifications were ambitious but achievable. 35.2 kilonewtons of thrust, 910 seconds of specific impulse, and an operational lifetime of 1 hour, 3,600 seconds of continuous burn time. That might not sound like much, but for deep space maneuvers, an hour of thrust from a nuclear engine could accomplish what would take days or weeks with chemical propulsion. The theoretical work was brilliant. The engineering was sound, but theory and practice are separated by a chasm that can only be crossed through testing, and testing a nuclear rocket engine requires facilities that most nations cannot even contemplate building. The chosen location was the Semipalatinsk test site in Kazakhstan, a vast expanse of steppe that had already been contaminated by hundreds of nuclear weapons tests. If anywhere on Earth could be considered expendable for nuclear experimentation, this was it. The test stand was a massive concrete and steel structure, engineered to contain, theoretically, even a reactor meltdown. Radiation monitoring stations ringed the facility in concentric circles, their sensors calibrated to detect the slightest anomaly in neutron flux or gamma radiation. But as Konyukhov's team prepared for actual testing, they confronted an uncomfortable truth. They were operating at the edge of human knowledge. Every calculation, every safety protocol, every emergency procedure was based on models and assumptions that had never been validated at this scale under these conditions. They were about to pump cryogenic liquid hydrogen through a functioning nuclear reactor, creating temperatures and pressures that existed nowhere else on Earth outside of weapons tests and stellar interiors. The first tests weren't even nuclear. Before you dare to achieve criticality, you run cold flow tests, pumping hydrogen through the system without initiating the nuclear reaction, checking for leaks, validating your instrumentation, making sure the basic plumbing works. These should be routine. They should be safe. They were anything but. The reality of working with liquid hydrogen at these scales and pressures proved far more treacherous than the models predicted. Hydrogen is the smallest molecule. It finds leaks that would contain any other substance. It diffuses through materials that seem solid, and when it mixes with air and finds an ignition source, it explodes with terrifying efficiency. The engineers knew this intellectually, but knowing something in theory and experiencing it in practice are entirely different things. Despite the setbacks, despite the growing awareness that they were dancing on the edge of catastrophe, political pressure demanded results. The program had consumed enormous resources. The leadership wanted vindication, and in 1985, the RD-0410 would finally face its ultimate test. A full-power nuclear burn that would either validate years of work or confirm the skeptics' worst fears. Konyukhov watched from the control bunker, separated from the test stand by thick concrete and several kilometers of contaminated steppe. His life's work was about to be validated or destroyed. Around him, technicians monitored instrument panels, their faces illuminated by the glow of readouts and oscilloscopes. Everyone understood what was at stake. This wasn't just a test. This was the moment that would determine whether the Soviet Union could claim technological superiority in the most demanding arena of space propulsion. The test sequence began with the careful ballet of achieving criticality. Control rods withdrew from the reactor core in precise increments, allowing the neutron flux to build gradually. Temperature sensors tracked the rising heat in the fuel elements. When the reactor reached operating temperature, liquid hydrogen began flowing through the cooling channels in the moderator, then through the fuel elements themselves. What happened next was, by any measure, a triumph of engineering. The RD-0410 achieved a specific impulse of 910 seconds, definitively surpassing the American NERVA program's best performance of 850 seconds. That 7% advantage might sound modest, but in the mathematics of rocket propulsion, it translates to dramatically reduced propellant requirements. For a Mars mission, that difference could mean the distinction between a mission that requires 2 launches to assemble in orbit and one that could depart from a single launch. It could mean the difference between a spacecraft that masses 800 tons and one that masses 600 tons. It could mean the difference between a mission that's theoretically possible and one that's actually affordable. The reactor temperatures exceeded 3,500 Kelvin, in some regions of the core, approaching 3,700 Kelvin. To put that in perspective, the surface of the Sun is about 5,800 Kelvin. The RD-0410 was creating conditions inside its reactor core that were more than half as hot as the surface of our star. This was hotter than the melting point of tungsten, one of the most heat-resistant materials known to science. The fact that the fuel elements maintained their integrity at these temperatures represented a genuine breakthrough in materials science and nuclear engineering. The engine ran for its planned duration, demonstrating stable operation and controllable thrust. The hydrogen exhaust, superheated to temperatures that turned it into a plasma, screamed from the nozzle at velocities that pushed the boundaries of what measuring instruments could track. Every sensor, every data point, confirmed what the engineers had calculated. The RD-0410 worked. It was real. The Soviet Union had built a nuclear rocket engine superior to anything the Americans had achieved. But in the immediate aftermath, As champagne bottles were being prepared and congratulatory telegrams drafted, Konyukhov's team was examining the post-test data with growing unease. Radiation monitors had detected unexpected neutron flux patterns during the burn. The distribution wasn't quite what the models had predicted. Something in the reactor core wasn't behaving exactly as designed. When they could finally approach the test stand and begin inspecting the engine, the source of the anomaly became clear. Several fuel elements showed microscopic cracks, stress fractures caused by the extreme thermal cycling and neutron bombardment. The cracks were tiny, barely visible even under magnification, but their implications were enormous. If the test had run just 20% longer, those cracks could have propagated. A fuel element could have ruptured. And a ruptured fuel element in an operating nuclear thermal rocket is the beginning of a nightmare scenario. Loss of structural integrity leading to uneven cooling, leading to localized overheating, potentially triggering a cascade failure that could result in a partial reactor meltdown. The success had been real, but it had also been a near catastrophe averted by luck and conservative test planning. They had proven the concept worked, but they had also proven that their margins were far thinner than anyone wanted to admit. The environmental monitoring told an even more sobering story. Post-test analysis revealed significant radioactive contamination of the test site, far exceeding predictions. Isotopes that would remain hazardous for decades had been dispersed across the steppe. The models had underestimated how much radioactive material would be released during operation. Medical monitoring of test personnel showed elevated radiation exposure levels. Several technicians developed symptoms consistent with acute radiation syndrome, though thankfully not at life-threatening doses. These were the people who had believed the safety protocols would protect them, who had trusted the calculations that said the exposure levels would be acceptable. Yevgeny Velikov, the Kurchatov Institute physicist who had provided crucial nuclear expertise to the program, found himself compiling an internal report that became increasingly difficult to write. The data was unambiguous. The RD-0410 worked, but only barely, and only under controlled ground conditions. The fuel elements could survive a 1-hour burn, but showed signs of degradation that suggested they couldn't survive the multiple burns that an actual Mars mission would require. The radiation release was manageable at a remote test site, but what would happen if such an engine failed during launch, scattering radioactive material across a populated area? The fundamental problem was one of materials science. No known material could withstand the combination of extreme temperatures, intense neutron bombardment, and thermal cycling for the extended periods required for actual deep space missions. You could make it work once, maybe twice, under ideal conditions. But the reliability needed for human spaceflight, where failure means not just a lost mission, but dead cosmonauts, remained out of reach. Velikov's report documented these concerns with scientific precision. He recommended against flight testing without major design revisions that would essentially require starting over, developing entirely new materials, rethinking the fundamental architecture of the engine. The report was classified immediately. The environmental monitoring data was never shared with local populations living downwind of Semipalatinsk. The medical data on exposed workers was buried in archives that wouldn't be opened for decades. Meanwhile, 8,000 kilometers away, American engineers who had worked on NERVA were reaching eerily similar conclusions. The parallel is striking, almost uncanny. Two superpowers, ideologically opposed, competing fiercely for technological supremacy, independently developing similar technologies, and independently discovering the same fundamental limitations. The American NERVA program had conducted multiple test firings at the Nevada test site between 1964 and 1969, achieving specific impulse values between 825 and 850 seconds with their hot bleed cycle design. Like their Soviet counterparts, they had encountered fuel element cracking, materials degradation, and concerning radiation release. Unlike their Soviet counterparts, American engineers had to contend with a growing environmental movement that made nuclear testing increasingly politically toxic. Nevada test site contamination became a public controversy. Activists demanded transparency, Scientists who had worked on nuclear weapons programs were beginning to speak out about the long-term health effects of radiation exposure. In 1972, the NERVA program was officially canceled. The public explanation cited budget cuts and shifting priorities. NASA was moving away from ambitious deep space missions and focusing on the Space Shuttle program. But internal NASA documents revealed that safety concerns were a major factor in the decision. The engineering margins were too thin, the consequences of failure were too severe, and the political will to continue testing nuclear rockets in Earth's atmosphere was evaporating. The Soviet program continued for more than a decade after NERVA's cancellation, but it was following a parallel trajectory toward the same conclusion. The laws of physics and materials science don't care about political systems. Both sides hit the same technological wall. Both sides discovered that while nuclear thermal rockets could work in principle, the gap between principle and practice was filled with radioactive hazards, materials science challenges, and safety concerns that couldn't be wished away through ideological conviction or national pride. The RD-0410 represented the pinnacle of Soviet nuclear rocket development. It achieved specifications that exceeded American capabilities. It demonstrated that Soviet engineering could match and surpass Western technology in one of the most demanding fields of aerospace development. But it also demonstrated the limits of what Cold War-era technology could safely accomplish. The Kurchatov-Mars 1994 mission concept, a nuclear thermal rocket-powered spacecraft that would carry cosmonauts to Mars and back, remained on the drawing boards. The engine existed, the test data existed, the political will existed, but the fundamental problems remained unsolved. How do you make fuel elements that can survive multiple burn cycles? How do you ensure that a launch failure doesn't scatter radioactive debris across a wide area? How do you convince the international community that launching nuclear reactors into space is acceptable? These questions didn't have good answers in 1985, and the collapse of the Soviet Union in 1991 ensured they wouldn't be answered by the program that had come so close to making nuclear space propulsion a reality. The RD-0410 program was quietly terminated. The test data was classified. The engines that had been built were placed in secure storage. The engineers moved on to other projects or retired, carrying with them the knowledge of what they had achieved and what they had narrowly avoided. Today, the RD-0410 exists in a strange liminal space in the history of space exploration. It was a genuine technological achievement, a machine that worked, that exceeded its design specifications, that demonstrated capabilities that remain impressive even by modern standards. But it was also a cautionary tale about the dangers of pushing technology faster than our ability to control it safely, about the environmental and human costs of Cold War competition, about the gap between what we can build and what we should build. The dream of nuclear thermal propulsion hasn't died. Modern programs are revisiting the concept, armed with better materials science, more sophisticated modeling, and a deeper understanding of the challenges. But they're building on the lessons learned by the engineers who built NERVA and the RD-0410, lessons purchased at the cost of contaminated test sites and exposed workers, lessons written in classified reports and declassified decades later. The Soviet nuclear rocket that beat America was real. It worked. It represented a genuine triumph of engineering and scientific ambition. But it also revealed a truth that transcends Cold War politics. Some technologies are so powerful, so dangerous, that building them successfully is only the first challenge. The harder challenge is building them safely enough that we can actually use them. And in 1985, on a frozen morning in Kazakhstan, Soviet engineers discovered that they had won the race to build the better nuclear rocket, but they hadn't yet solved the problem of how to fly it without gambling with consequences that could dwarf any triumph. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.